Bismillahirrahmanirrahim. Assalamu alaikum, students. Last time we discussed the idea of capacitor and capacitance, and we calculated the capacitance of a parallel plate capacitor. So we will continue with the calculation of capacitance. So I write calculating the capacitance so we continue. So I write continued. So last time we showed that capacitance of a parallel plate capacitor is epsilon naught A by D. This was for parallel plate capacitor. Epsilon naught is permittivity of free space. A is area of the plates of the capacitor. D is plate separation, right? And we assume there is vacuum between the plates. That much you know. Now we take the second one. Cylindrical capacitor, right? I want to calculate now the capacitance of a cylindrical capacitor. Now, cylindrical capacitor consists of two coaxial cylinders like this. Right? So it has some length. A is the radius of inner cylinder. Let me use another color here. B is the radius of outer cylindrical shell. So in case of this actually solid cylinder. So in case of cylindrical capacitor, we have a solid cylinder with radius A and length L. Then it is coaxial with another cylindrical shell with radius B and length L. And this is empty space between the two cylinders, right? So is the radius of inner solid cylinder. B is the radius of outer cylindrical shell. L is length, right? We show first this diagram in cross section. So it's like this. So this is V, this is E. Then we charge the capacitor. This inner solid cylinder is positively charged, and the outer plate is negatively charged. Right? So Q charge is on this, and it is understood there is minus Q on the outer cylindrical shell. Now I show the lines of force. So when we charge the capacitor, electric field lies in the space between the plates. These are lines of force, right? This is electric field. The first step of our calculation is, remember, this is in cross section. You are looking from this side or this side on the charged cylindrical capacitor. Now, when we select our Gaussian surface, let me use this color. This is what? This is a cylindrical Gaussian surface with radius r and length L. So it is enclosing the inner solid cylinder having positive charge Q on it, right? And this cylindrical Gaussian surface is obviously coaxial with the cylinder. So I use some other color. Let me use this. So what is the radius of this? R. Now I show the path of integration. With which color? I think this one. This is my make it thick path of integration, right? And we're assuming L is much greater than B. When L is much greater than B, we can neglect the fringing of the electric field that occurs at the ends of the cylinders. Now, applying Gauss's law to our Gaussian surface, applying Gauss's law, it says closed integral E dot dA is Q by epsilon naught. See, Q is the charge inside the Gaussian surface. So Q is Q because our Gaussian surface encloses the positive charge Q, which resides on the inner solid cylinder. So Q is Q. Now remember, uh, the electric flux will be contributed by only curved walls of the cylindrical Gaussian surface. There will be no flux penetrating through the end caps. And second, electric field is constant over the curved walls where they are equidistant from the center, and electric field and area vector everywhere over the curved walls is parallel. Theta is 0. So it will be simple integral. It will become closed integral eta equal to q by epsilon naught, because theta is 0 and cos and cos 0 degrees 1. Then I can take E out. Now closed integral dA is q by epsilon naught. It will be 2 pi r L, because closed integral dA is 2 pi r L, which is surface area of the curved walls. So we solved for the electric field. So electric field is q by 2 pi epsilon naught LR. I name it first, right? So electric field is q by 2 pi epsilon naught LR. Now, then our next step is V is the magnitude of the potential difference between the plates. And we write it plus to minus ETS. I've already explained it how. We are taking path of integration from positive plate to negative plate. So electric field is similarly directed. E dot ds becomes just ETS. Then negative in this equation was basically this equation VB minus VA is minus E to B E dot ds. Now when we take path of integration from positive plate to negative plate, this integral will be negative. And we said we take only the magnitude of potential difference. This is magnitude of potential difference. So negative will be absorbed in that. So just plus to minus EDS. Substitute the value of E, which is q by 2 pi epsilon naught LR. Now ds is dr. On the r, limits will be a to b, because at the surface of first cylinder r is a, and we move to the surface of the second cylindrical shell, second plate of the capacitor, where r is b. So just a to b, right? Use another color. Here we are saying ds is dr. Well, we are moving radially. Our displacement is radial. R is variable of integration. Rest is constant. So I take q 2 pi epsilon naught L outside is A to B dr by r, right? So it is just natural logarithm of r when we integrate it. I write it directly, this q by 2 pi epsilon naught L ln of b by a when you solve this integral, right? So v is q by 2 pi epsilon naught L natural logarithm of b by a. I write it this way, or q is 2 pi epsilon naught L by ln of b by a times 2 pi epsilon naught L by ln b by a times v. This is my second. So I have rearranged this equation simply. I have taken 2 pi epsilon naught to this side, ln b by a, the downstairs on the left hand side. So I got this q is pi epsilon naught L over ln b by a. Next step is comparing equation 2 with q is equal Cv, which is the defining equation of capacitance. We get C is 2 pi epsilon naught L over natural logarithm of b by a times this, only this. This is my expression, right? 2 pi epsilon naught L over ln b by a, right? So if we have a cylindrical capacitor of length L inner radius A, outer radius B, L being much greater than outer radius B, and there is vacuum between the plates, then equation 3 gives the capacitance. So this was our second capacitor, cylindrical capacitor. Now we move to third one. Spherical capacitor. Spherical capacitor. Now in case of spherical capacitor, we have a solid sphere, radius E, enclosed by a spherical shell of radius B, right? So I show a diagram in cross section like this. Let me make it a bit bigger. These are concentric. So I have inner solid sphere of radius A, outer spherical conductor is concentric to inner one of radius B. So A is a radius of inner solid sphere, B is radius of outer spherical shell. Again, we charge it, the capacitor. So we have positive charge on the inner plate, and there will be negative charge on the outer plate. To charge, there is electric field between the plates like this. Right, this is your charge Q. So this is my electric field. Now we take a spherical Gaussian surface concentric with the spherical capacitor. So let this be my Gaussian surface. So this is what? Spherical Gaussian surface with radius r. So let me show its radius. Its radius is r. And let us show the path of integration. We are moving from positive plate to negative plate. This is my path of integration, right? So this is the figure in cross section. So we have inner solid sphere of radius A, outer spherical shell of radius B. Then we charge the capacitor. Q charge resides on inner solid sphere, minus Q will reside on the outer spherical shell. Electric field lies between the plates. Then we take the path of integration from positive plate to negative plate, and we take a spherical Gaussian surface concentric with the capacitor with radius r. Right? Applying Gauss's law. Applying Gauss's law. Closed integral E dot dA is Q by epsilon naught. Again, Q is Q. There is charge inside the Gaussian surface, which is Q, and electric field over the Gaussian surface is constant. It can be taken out. E dot dA is just ED. So it will become closed integral EdA is Q by epsilon naught cos theta is 0 degree. Theta is which angle between electric field and area vector. Then E can be taken out. It will be this, and I can write E 4 pi r square is equal to Q by epsilon naught, because closed integral dA is 4 pi r square, which is surface area of Gaussian surface, which is spherical, right? So we got the electric field. So our electric field is 1 by 4 pi epsilon naught q by r square, right? 1 by 4 pi epsilon naught q by r square. This is my first. So the next step, we solve for the electric field, right? Then use another color. Now magnitude of the potential difference between the plates is plus to minus ETS. Using first for electric field is plus to minus 1 by 4 pi epsilon naught q by r square. I replace ds by dr because we are moving radially. ds is dr, right? A variable of integration is r. Therefore, what are limits on the integral? E to b 1 by 4 pi epsilon naught q by r square dr, right? 1 by 4 pi epsilon naught q by r square dr e to b. So I take the constant out. It will be q by 4 pi epsilon naught integral a to b 1 by r square dr, right? q by 4 pi epsilon naught integral 1 by r square dr. So I use this space here. So when you solve this integral, you will get v equal to q by 4 pi epsilon naught 1 by a minus 1 by b q by 4 by epsilon naught 1 by a minus 1 by b. Check it right here. Check it. So again, I did this way. Q by 4 pi epsilon naught ab upstairs. I write b minus a. Right. So I write it. I rearrange it. Q is 4 pi epsilon naught ab will come up and b minus a will be downstairs times b. This is my second equation, right? Q is 4 pi epsilon naught ab by b minus a, right? So comparing second with Q is equal to C, we get C is 4 pi epsilon naught ab by b minus a. This is my third, and this is my required expression, right? So if I have a spherical capacitor with inner radius a and outer radius b, and there is vacuum between the plates, then its capacitance is given by 4 pi epsilon naught ab by b minus a, where a is inner radius and b is outer radius. This was our, so we calculated the capacitance for parallel plate capacitor first, this one, then cylindrical capacitor, and now spherical capacitor. This one. Now we have an isolated sphere. Isolated sphere. We can associate. We can associate capacitance to an isolated solid sphere. How? See, we can associate capacitance and isolated solid sphere this way. In spherical capacitor, we said we have inner solid sphere of radius A and outer spherical spherical shell with radius B. We can let B tending to infinity. So that our second plate is at infinity, then the capacitance of the capacitor will be simply associated with the capacitance of inner solid sphere. I repeat, if we let B tending to infinity, the capacitance of the system will be simply associated with the inner solid sphere of radius A. If we do that, we write let V tends to infinity. Then this equation I write first. C equal to 4 pi epsilon naught AB by B minus A. 4 pi epsilon naught AB by B minus A. So if B tends to infinity, that means B is a very large compared to A here. In this denominator, A can be neglected. This B will cancel out. Then this I write the equation this equation reduces to C is 4 pi epsilon naught A, right? Or let A be equal to R. So let C is 4 pi epsilon naught R. That means if I have a solid sphere of radius R, then its capacitance is given by 4 pi epsilon naught R, right? So this was our calculation of different capacitances. Now I want to refresh your memory by certain ideas. First, capacitors in series and parallel. You have done it. I just refresh your memory. We know circuit symbol for capacitor is this: two bars of equal length. This is the circuit symbol of a capacitor. First I write capacitors connected in parallel. So if I have two capacitors connected across points A and B, this way their capacitances C1 and C2, they are said to be connected in parallel across points A and B. If we want to replace these two capacitors by a single capacitor without having any impact on the circuit, that means we want to substitute this combination of capacitors across points A and B, then we use a single capacitor instead of this combination, which we call C equivalent. Right? So equivalent, C equivalent is the capacitance of a single capacitor, which replaces this combination. Now, how we obtain it? C equivalent is simply sum of C1 and C2. So in parallel connection, the equivalent capacitance is obtained by just adding the individual capacitances. So in general, if there are 10 capacitors connected in parallel, then this is for 2. Here I write equivalent capacitance for n, summation small n running from 1 to capital N, Cn. That means we have to simply add all the capacitors, all the capacitances in the combination, that is C1 plus C2 plus C3 up to Cn. Then if we have capacitors, this was my A, capacitors connected in parallel, capacitors connected in series. If I have two capacitors connected in series this way, the capacitance is C1 and C2. This is the series connection. Capacitors are connected across points A and B this way. They are said to be connected in series, right? And C equivalent is shown this way. Now, how we get C equivalent? This is the expression. I write them directly, I don't derive them, because I know you know them. So here 1 by C equivalent is 1 by C1 plus 1 by C2. That means if you have to find the equivalent capacitance, you have to first reciprocal individual capacitances, then add those reciprocals, then you have to reciprocal the result, right? This for two capacitors. In general, for n capacitors connected in parallel, we have 1 by C equivalent is summation n equal to 1 by n equal to 1 to capital N, 1 over Cn. That means you have to add 1 over C1 plus 1 over C2 plus 1 over C3 up to 1 over Cn to get 1 by C equivalent. Then you can get C equivalent by the reciprocal, right? Now I will give you some homework. This is now your homework. Question 1. How many one microfarad capacitors must be connected, must connected in parallel to store a charge of 1 coulomb with a potential of 110 volt across the capacitors, across the capacitors. I repeat the question. How many 1 microfarad capacitors must be connected in parallel to store a charge of 1 coulomb with a potential of 110 volt across the capacitors? And remember, 1 microfarad is 10 raised to minus 6 farad. Now question 2. Okay, this is question 2. The plates of a spherical capacitor, the plates of a spherical capacitor have a radii 38 millimeter and 40 millimeter, right? Now part A, calculate the capacitance. Calculate the capacitance. Part B, what must be the plate area? What must be the plate area of a parallel plate capacitor with the same plate separation, with the same plate separation and capacitance I repeat the question. The plates of a spherical capacitor have radius 38 millimeter and 40 millimeter. Part A, calculate the capacitance. Part B, what must be the plate area of a parallel plate capacitor with the same plate separation and capacitance. Remember, I'm just refreshing your memory. 1 millimeter is 10 raised to 1 minus 3 meter, right? Let's move to next question. Question 3. A 6 microfarad capacitor is connected in series with a 4 microfarad capacitor. Potential difference, a potential difference of 200 volt is applied across the pair. Part E, calculate the equivalent capacitance. Part B, what is the charge on each capacitor? Part C, what is the potential difference across each capacitor? Repeat the question. A 6 microfarad capacitor is connected in series with a 4 microfarad capacitor. Potential difference of 200 volt is applied across the pair. Part A, calculate the equivalent capacitance. Part B, what is the charge on each capacitor? Part C, what is the potential difference across each capacitor? That's all for today. Do your homework. Don't waste your time. And don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.